Okay, welcome back. Update number one. Um, it took me a little longer to get around to doing this than I was hoping, but anyways, in the future, my goal is to try to do an update video every like Friday or Saturday. But anyways, I'm not so sick anymore. I still have kind of a lingering cough every like 6 hours, but anyways, so what's happened? Um, so I've been doing some studying, and I found that a lot of the information in this book is not really relevant to my project, as might have been expected if I was a little sharper. But anyways, there's a lot in here about solid rocket motors, solid propellants, and so I just kind of skipped that stuff. I just tried to filter through, find all the information that I really needed, and spent a lot of time in chapter 3, which is titled Nozzle Theory and Thermodynamic Relations. So, anyways, most of I'll be talking about it today, but most of what I've been working through and applying has come from this chapter. But chapter 3. Anyways, so kind of the first step was to decide on propellants. Again, I want to go with liquid fuel, both because that's awesome and because it's probably a bit better for my intentions, because I need to be able to like throttle and thrust vector control. So I started getting thinking. I have lots of options for fuel, but I found that my options for oxidizer were far more limited. I don't want to mess with cryogenics, at least quite yet, so that narrows down my options pretty quickly right there. Non-cryogenic liquid oxidizers. And I eventually decided on hydrogen peroxide. That has been used professionally in like real rockets. Although it's going to be kind of dangerous. It needs to be very high concentration, which is a problem. But I found this website called Lab Alley. This company, I can probably just order some online. I think they have an option that was like 34-35% concentration. And after doing some math, that hopefully checks out. I'll be walking you through some of it today. And then for fuel, I could have chosen a bunch of things. I ended up going with isopropyl alcohol. Could have also done ethanol or like literally anything else. I don't know. But I figured why not? It'll do the trick, I think. It should burn pretty cleanly, hopefully, as opposed to like gasoline. I'd probably get a lot of soot if I did gasoline, I'd imagine, because the molecules are probably bigger. Anyways, so that's what I decided on. As high concentration as I can get of hydrogen peroxide with isopropyl alcohol. And so the next step was to balance the equation, the chemical equation, which you can see at the top here. And so all this water here is because the hydrogen peroxide is going to be so diluted, so there's going to be all this extra water, but it's going to react and then hopefully give me a good amount of heat. Page about 150 to 158, 159 in Rocket Propulsion Elements. I have the 9th edition. That's where it talked about how to calculate the combustion chamber temperature. I forget what it's called. There's a certain value assigned to each chemical compound, and you basically like sum it up on each side of the equation and like take the difference, and that's how much energy will be absorbed. And so in this equation, it was actually a negative number because it's releasing energy, not absorbing energy. Blah blah blah. The number I got was about 888 Kelvin for my combustion temperature. Like I said, I've also been consulting with a few AI models such as Claude and ChatGPT and Grok. um, and Claude found a value of about 820, I think. So somewhere around there, I decided I'll probably just round down to 800, um, the at least for like expectations, because it's not going to be perfect, especially with all this water getting in the way of the combustion. uh, I mean, it would like slow it down. I mean, anyways, I don't know, but in terms of my chamber pressure, I have a goal of like about 100 psi. That would do the trick, but even a little less, I think I can make do with that. But my goal is 100 psi, which would be about 690 kilopascals. So yeah, and then what else we have here? Oh yeah, so the first step was determining the value of K, or the next step, I guess, was determining the value of K um, for my propellant or exhaust combination or whatever, which has to do with like specific heats or something. It's the ratio between the specific heat at constant temperature and the specific heat at a constant pressure and specific heat at constant volume. That's what it was. It's the ratio between those, and it's useful for doing all sorts of calculations. And so I had to find these values for my compounds for hydrogen. Wait, what am I talking about? For water and for CO2, right? So water and CO2 are going to be my my exhaust components, my my products of the reaction. And so to find the temperature, or whatever K is, to find the K, I have to find, this is specific heat at constant pressure of water, specific heat at constant volume of water, specific heat at constant pressure of CO2, and specific heat at constant volume of CO2. And I sort of took the weighted average. I think that's how you do it. You take the weighted average of each and find the ratio there. And so I got a K value pretty close to 1.3. So yeah, and then with this information, I could then do a calculation of, or sort of estimate my exhaust velocity of the exhaust, which came out to be around, I think, like 1,020 meters per second, which is pretty solid, I think. I mean, that's kind of a lot when you think about it, like a kilometer per second. So nice. And if, I'm not really sure exactly how much the final thing is going to weigh, what the wet mass is and the final mass is, or how fast I want it to accelerate and decelerate and such. But to estimate, let's say I want it to do about 20 newtons of force, then divided by 1,000 meters per second for the exhaust velocity means I will need a flow rate of about 20 grams per second. So yeah. Oh yeah, right down here, for doing some other calculations, I need to know the average molar mass of the exhaust, which, as you can see, is pretty close to the molar mass of water because the exhaust is mostly water. It's like 3 parts CO2 and like 46 parts water. So anyways, and then R, specific R, as in, so this is not the universal constant R in the ideal gas law. Oh yeah, another class I took in high school that I didn't think about how useful it would be is chemistry. I'm very glad I took chemistry because there was a lot in here that I would have had a much harder time with if I hadn't taken chemistry. But so R is also useful for doing various calculations. I think this is like how much energy it takes to raise 1 kilogram by 1 Kelvin, effectively, of my exhaust. Blah, blah, blah. What else? So I've been doing all this math stuff. And once I figured that stuff out and that stuff out, the pressure and stuff, then there was an equation on page 56 to estimate the ideal or a good, was it the minimum or the maximum, or I'll have to double check it, but the throat area, the cross-sectional area at the throat of the nozzle, which came out to be this. That's pretty small, but it's in meters squared. So in terms of diameter at the throat, it's 0.3 no wait, I think that was radius, dang it. That's radius. 0.3 centimeters in radius at the throat. And then on the same page, next equation, 3-25, is an equation to figure out the expansion ratio, the ratio between the area at the nozzle and the area, cross-sectional area at the nozzle and cross-sectional area sort of at the rim of the nozzle. That came out to be about 1.66, which is like the smallest expansion ratio I've ever seen. But I guess it kind of makes sense because I have all this water, which is going to be like ruining everything, and it's going to be like really, I don't know, it's not very hot. I mean, in the grand scheme of things, this isn't a very high chamber pressure, and it's going to be only at sea level, approximately. Actually, I'm not very close to sea level. Never mind. So yeah, I have all this stuff. And then, oh yeah, on page 101, it's got the rocket equation, and so with my exhaust velocity. So, oh yeah, so right here, right here. If I assume I want like 20 newtons of force with 1,000 meters per second of exhaust velocity, then that means it will need a flow of 20 grams per second, or 0.02 kilograms per second. I don't really know, again, exactly all the precise details of what my flight profile is going to be like, but I mean, like, to say, like, the estimate is like, let's say it's probably going to be around 250 seconds of burn time, and it's not going to be all at 20 newtons. But that's like a very rough estimate, and we'll kind of see how things go as testing moves on and as things get built and stuff. But if we just say it needs to burn at 20 newtons per second for, 20 newtons for 250 seconds, then that means I need 5 kilograms of propellant. And if I allot myself 5 kilograms for the rest of the rocket, which I don't know if that's too high or too low yet again. If I do that, then that means that the rocket equation tells me I will have almost 700 meters per second of, oh, there you go, almost 700 meters per second of delta V, which is pretty good, I think. Hopefully that's enough for what I need. But, so, yeah, that's about where I'm at, I guess. Another question was how big I need to make the thrust chamber, the combustion chamber, and there wasn't very much in there about that, although later on page like 287 it talked about how you want to make sure the chamber is big enough that the propellant has enough time to fully combust before leaving, and it gave an equation that relates sort of the stay time within the chamber to how big it is and like the mass flow rate and stuff. And I figured I'm probably going to want a large stay time because of how much water is going to be getting in the way and because of how small my flow rate will be. But I don't really know what to expect. You know, I think that's, again, the kind of thing where I mean, testing will play a big role, I guess. But anyways, I can kind of use that as an estimate, but it didn't really talk about limits on making it too big, on like why you couldn't just make it like as big as you want to make sure it's all burned. So I don't know, I'm gonna have to do more research, I guess. But anyways, so yeah, this is kind of like the bare bones theoretical skeleton of how things are gonna go down, I guess, of the propulsion propulsion system. But uh, next, I think I can start 3D modeling stuff now. So one thing I want to do is I want to research what CAD softwares are commonly used in industry, by like SpaceX, uh, or Rocket Lab, or some other big company or something. See what softwares are common and try to use that if it's not too expensive, so I can gain experience with something that they probably care a bit more about. Um, I've used Blender a little bit in the past for like random projects, but I don't know. I don't know. I'll see if I can find something that might look a little bit better on a resume. um, what else? Uh, yeah, so I can start 3D modeling. Oh yeah, so um, the semester is getting kicked off. I'm not starting classes yet. Uh, I'll start classes in the fall. I think I said that last time. But I'm joining my college's, my university's rocket club. Um, they have a rocket club, and so I think I could get a lot of useful information from that. We had our first meeting on Wednesday, and it was just sort of a kickoff meeting. But I learned about this software called Open Rocket that may or may not be useful for designing things. So that's another thing on the to-do list, is investigate this software, maybe other softwares that might be handy for designing things. Um, Another thing I need to do is I need to see if I can get this bad boy working. My 3D printer uh, has not been in tip-top shape. For some reason, the print head won't extrude the filament unless I like stuff it in there really hard. So it's not like plugged, but it's like not working. So I'm gonna like take it apart and see if I can fix it somehow. If not, and even if I can fix it, then either way, my dad also has some 3D printers at his studio. He's got an FDM printer that prints like up to a meter high or something like that. So that's pretty cool. That is like probably what I need. He's also got a couple SLA printers, which will probably be very useful. Um, so, but yeah, that's another thing I need to, that's on the to-do list. And what else? Oh yeah, so I also looked into feed systems to pump the propellants into the combustion chamber. And there are a few options that the book talked about. There's like a turbo pump, and like do a real like engine cycle where you like burn a little bit of the fuel to spin the pump to pump more fuel. That's probably a little too complicated for me, but at least for this project, maybe next time. But since I'm on a time crunch, um, I did a little bit of research into electric pumps that I might be able to use. I checked all over just like crazy random websites that I've never heard of to find. I found several pumps that would give me the pressure I need and the flow rate I need. And of course, if I want my chamber pressure to be 150 psi, then the pump needs to go a little more than that because there'll be pressure losses in like the tubing and the valves and everything, and the injection plate. But anyway, so I looked into that. I found this one that looked pretty good on Amazon. It was like pretty light too, so it wouldn't be weighing down the rocket. But it wasn't. I mean, the main concern with that would be if it would be able to handle the high concentration of hydrogen peroxide. And so I sent an email to the company asking if it would be able to handle 35% concentration hydrogen peroxide, and they responded by not answering my question and just saying that they didn't recommend using higher than 10% chemicals, 10% concentration of chemicals. So that wasn't very helpful. So I kind of gave up on that idea, and so I think I'll go with a pressure-fed system. There are a couple options. There are like two main options that it talked about in this book. rocket propulsion elements. One was like called a blowdown system, and I can't remember what the other one was. But basically, one way is you pressurize the tanks really high before launch, and then you just like let that pressure pump out the propellants. But the downside is that as the propellants empty, the gas expands and it's lower pressure, which might be fine because you don't need as much thrust as it's getting lighter and lighter. But the other option was to have another tank, a very high pressurized gas that would slowly pump more and more gas into the propellant tanks to keep it at the same pressure all the way through. And I'm probably going to go with that way, that latter way, because it allows me to, well, I mean, I think it would make it easier to control the thrust more finely and stuff. But I still need to figure out what all that would entail. Anyways, so yeah, a few things to do. I need to figure out what tanks can hold the kind of pressures I need, both my propellant tanks and for the pressurized gas tank to fill the propellant tanks. I might be able to just get like a couple like pressurized CO2 cartridges that you can like pump up your bike tire with, or like something like that. I also need to design an injection plate. I need to figure out some good injector designs. I was watching this YouTube video by Scott Manley, and he said that this one is really good called coaxial swirl injector. That's what it was. Anyways, so I don't know, maybe it probably doesn't matter that much. Probably just do something simple. He also talked about, or no, maybe it was Everyday Astronaut that mentioned this design where it's like you can kind of pull it in and out to like use it also for like throttling. So that might be handy, or maybe it'd be easier just to have some kind of valve to throttle. I don't know. There's a lot of decisions that still need to be made. But that's I guess about where I'm at. What needs to get done next week. I'll get as much of that done next week as I can. There are a few more chapters in here that I should probably look through. There's like a section on thrust chambers, which says a bit about injectors. I've read through some of that part already a little bit. Start an ignition. Yeah. I glanced through some of that, but it'd be good to go through it again. Given nothing about solid rocket propellants. Engine systems, controls, and integration. That's another chapter I need to read. I saw this part where it talked about various gimbal systems, thrust vector control systems, which I will probably need. So I'll look at that again. And then last chapter, chapter 21, rocket testing. Oh yeah, there's the thrust vector control, chapter 18. So, yeah, there are a few more things I need to research so I can figure out. Well, I'm gonna obviously, like I said, my philosophy is to try to be a bit more like SpaceX than like NASA, in that I just like build something as fast as possible to get it running, because that's gonna teach me what I need to know the most. And instead of like doing all sorts of math and theoretical work and simulations beforehand to like make sure it works right the first time, because it's probably not gonna work right the first time anyways. So that's kind of that's my philosophy, I guess. And hopefully that'll lead to more rapid innovation and iteration. I was thinking I can probably start modeling. Like I said, I'm probably gonna need to 3D print the chamber and nozzle in metal with some like online service, and so I can probably like do that pretty soon. And then once I have the part, then figure out like what kind of chamber pressures and temperatures I'm working with, and what kind of force it can produce, and then kind of design the second iteration around what the engine is actually capable of instead of what it's just theoretically capable of. I'm going on a little too long now, but anyways, I guess I'll cut it off there. Well, hopefully I'll remember to post again next week. If I don't, then give all my videos a thumbs down.